So welcome everybody to this week's joint astronomical colloquium in Heidelberg. And we're very grateful to have Chris Harrison here to give the colloquium here. And I'm going to ask Marco to do the formal introduction. Thank you.
Thank you very much. I'm happy to have a lot of people here today in person. That's really nice. So I'm happy to present today Chris Harrison. He has finished, or he started his academic career as a bachelor student in Edinburgh University, which he finished at 29 with first-class honors. And then he moved to Durham University, where he completed his PhD in 2014, following up with a postdoctoral study or research. And then in 2017, he became a research fellow at the ESO here in Germany. And later, in 2020, he received an academic fellowship at the University of Newcastle, where he's still part of today, as an associate professor in astrophysics. And he's also part of the UK Research and Innovation for Future Leaders Fellows. So as you will see in the talk, Chris is very interested on galaxy evolution and active galactic nuclei. And during his career, he has achieved plenty of awards and led or collaborated with dozens of successful proposals and, of course, plenty of published papers. And he is also pioneering data accessibility projects for blind and visually impaired audiences, and has been recognized with multiple awards for these innovative and inclusive approaches for science communication and open research opportunities and practices. So with this, I'm happy to welcome Chris for today's talk.
Thank you. All right, so hello everyone. Thanks very much to Marco for the introduction, but a huge thank you to Marco for organizing my day. I'm not here very long. I've already been to the House of Astronomy, Ari, Peter, and here. I didn't even know there were that many institutes, so thank you for coordinating that for me. I'm delighted to give this talk. So I'm going to focus on galactic outflows driven by supermassive black holes. I've listed here the students and postdocs who are really the driving force behind the work, which includes Samuel Ward, who's just recently moved to Flatiron, Ivan Almeida, who just recently moved right here to MPIA in the audience, Vicky Fawcett, who's currently with us Newcastle, Huda Haidar, and Jerry and Gabrielle, who's based at ESO, or has just moved from the. And I understand there's a wide variety in the audience, including students, so I'm pleased to give a broad introduction to the topic. That's part of my goal, is to try and remove some of the confusion behind this topic. I hope I can do that for you today. And then I'll present two parts to the research that we're working on. The first part will be about how we're using simulations to help guide the interpretation of the observations, which is notoriously very difficult. And then I'll give some tentative, sort of interesting results about how luminous AGN might be injecting energy into the host gas. I'm not going to give you the answers. I'm probably going to open more questions, but I think there's some very interesting results nonetheless. But let's start at the beginning, of course. So we know quite clearly that galaxies contain supermassive black holes. Evidence becomes most strongly from our own Milky Way galaxy. If we track the stars, the motions of the stars at the center of our Milky Way galaxy has been done over a couple of decades. You see that they're orbiting around some massive, super dense, invisible objects, which is completely consistent with a supermassive black hole. If you take even more refined measurements, such as from gravity with a very large telescope interferometry, these precision measurements are perfectly consistent with this supermassive black hole being there. And of course, one of the most famous images coming out of astronomy in the recent times is from the Event Horizon Telescope, which shows you the material in the vicinity of the supermassive black hole, taken in millimeter wavelength, and there you see the shadow. Now, it's not just our own Milky Way galaxy, which has a black hole around 4 million solar masses. Of course, we see this in other galaxies, such as M87, which is where the first Event Horizon Telescope image came from. And in this case, we're talking about 6 to 9 billion solar masses black hole sitting there at the center of these galaxies. And it's all galaxies. If we go to the galaxies locally and we track their black hole mass using a variety of techniques, it can be how the gas is moving, how the stars are moving, and we plot it against some property of the host galaxy. Now, there are many different ways to plot this, and we could have a whole talk just on that. Here's a nice simple version where we have black hole mass versus bulge mass. So these are galaxies with well-defined bulges or elliptical galaxies. You see these tight correlations over several orders of magnitude. This is telling us something about the co-evolution of those black holes at the center of the galaxies and the galaxies in which they reside. Now, one of the most fascinating things about these black holes is when they're growing. And so hopefully the only acronym you have to remember for this talk is AGN, active galactic nuclei. And that means we have detected a growing supermassive black hole. This, of course, is an artistic impression. But when these black holes are growing, there's material flowing around them. This gets incredibly hot to form these accretion disks. Energy is released as radiation, you get winds off these accretion disks, and that radiation can be detected across the electromagnetic spectrum. If we detect that, we call it an active galactic nuclei, AGN. In addition to that radiation and wind, we have these collimated charged particles, we call these jets, most commonly seen in the radio emission, also in X-ray. What's really incredible about these black holes and the accretion process is how efficient the energy process is. So some fraction of that mass of that gas will fall onto the black hole and help it grow to become supermassive, but a large fraction of that gas mass will also be radiated as energy. And if you do some basic back-of-the-envelope calculations, the total energy released over the lifetime to grow that black hole is significantly higher than the binding energy of the galaxy which it resides, and it's comparable to the binding energy of the halo in it. If you can couple some of that gas, some of that energy to the gas, you have the potential to do some significant damage or at least alter the environment in which they live. And indeed, that's what we call AGN feedback, or at least for my purposes, that's what we mean when we say AGN feedback. If that energy that's released somehow influences the host galaxy or the larger scale environment, I'm going to call that AGN feedback. I'm going to give you one more term here, just for clarity. If I use the term quasar, all I mean is the most luminous AGN, the most rapidly growing black hole. So it is releasing a lot of radiative energy. Now, do we think this is important? Well, yes. In fact, it's a critical component of our understanding of galaxy evolution. All of our galaxy evolution models require that this AGN feedback process is there in order to explain observed properties that we see in the real universe. So I'm just going to take you through a schematic way of looking at this from one particular model, but if you take any model, basically you get the same answer. So let me talk you through this plot. This is stellar mass divided by halo mass on the y-axis as a function of halo mass. And you can think of this y-axis as how efficiently am I converting the baryons I have available into stars. So what's my sort of baryon to star conversion efficiency? If you take a model like this one from Somerville, you get this gray dashed line across the top here. This is a model with no feedback processes in. And you can see that it's significantly higher than the observed galaxy population, which is this green curve. Now, yes, it drops at the higher masses. This is just to do with the heating when you're forming these halos, but it's definitely over efficient if you have no feedback energy injection process. If you have a model where you include some sort of star formation, stellar feedback, you allow your star formation to inject energy into its surrounding medium. You reduce that efficiency at the lower halo masses to something more comparable to what we see in the real universe. So that's shown by this purple curve here. But we're still over efficient at the higher masses. This is where our AGN come in. If we inject energy from these AGN, you have that huge energy supply. You're able to suppress the efficiency at these higher halo masses towards something that looks more realistic. And that was a schematic from semi-analytic model, but this now is inside all of our cosmological models. Of course, here in Heidelberg, we're running such models. Here's a movie from the TNG simulation. It's color-coded by gas temperature, where green and blue colors are colder temperatures, red and white temperatures are hotter. And as these AGN are having these events, these AGN events are going off, you can see they're heating and moving gas in their surroundings. And it turns out it's not just about efficiencies. There are many observable properties of galaxies that end up being controlled, or at least some sort of required. This feedback process is needed to some degree to explain how galaxies look. And this includes galaxy sizes. The feedback is able to puff up these galaxies by redistributing the baryons. The distribution of metals inside the surrounding gas of these galaxies. Star formation rate distribution. So, for example, the color bimodality you see of galaxies, the blue population and the red population. All of these things, AGN feedback may be playing an important role. What I'm interested in is how we're moving this gas. And we're talking about these AGN-driven outflows. And here's some snapshots from one of Dylan's papers from the TNG, where we're seeing an AGN event, and it's heating and redistributing this gas. So we've got time going down. On the left, we're seeing the velocity of the gas. You can see the velocity being reached very high, thousands of tons per second. And then on the right side, we have temperature. So at the very center, moving up top down, we have the galaxy disk, but most of what you're seeing is dominated by the top gas, which is being heated and moved by the AGN event. So we have this underpinning need for AGN feedback in our understanding of the galaxy formation from a theoretical perspective and from our simulations. But what about observations? What can we do with our observations to test these ideas, refine these ideas? And these are the sort of questions an observer like myself, most of my background is in observation, might be asking. So for example, how and how efficiently is that energy being transferred from an AGN event into the surrounding gas? How do you get that energy in, and how efficiently is it happening? What are the outflow properties in the multi-phase gas? So this gas is in multi-phases. We have the gas distributed on different scales. What are the properties that I can measure in my observations of those multi-phase gas outflows? And can we find evidence for short and long-term impacts of this AGN feedback process if it's really going on? So I'm going to today focus on the first two questions, looking at how the energy is transferred, how efficiently, and what are the outflow properties in the multiple phases. Now, if you read the literature, observational literature on AGN feedback for the first time, I wouldn't be surprised if you end up feeling a bit like this. Like, what is going on? It's quite confusing. There are papers that appear to self-contradict themselves, different papers contradicting. So you might find papers that say there's definitely evidence for AGN feedback. Then you find another paper that says there's definitely no evidence for AGN feedback. You'll find papers that say the observed outflows are too inefficient to impact on star formation compared to model predictions. You'll find papers that say outflows are rapidly depleting star-forming material, and it goes on and on with these contradictions. And on top of that, you have an array of confusing terminology in the literature about different modes, different ways of defining AGN, radio loud, radio quiet, jet driving. All of these terms are definitely confusing, and I don't blame you if you get a bit confused if you're approaching this for the first time. So with that in mind, I attempted with my colleague, Cristina Ramos-Almeida, to try and simplify it for you. So we wrote this review last year called Observational Tests of Galactic Nuclei Feedback, an overview of approaches and interpretation. We tried to simplify some of this, and our aim is, after reading that, you feel a little bit more like you understand what's going on, but feel free to tell me if that's not the case. In that review, you'll find there's loads of citations, so the talk will be fairly citation-light, but there's hundreds of citations in there if you want to dig into the literature. In that review, we try to break down these observational approaches into four main categories. People who are trying to approach the feedback problem from different perspectives. So this flowchart kind of tries to bring all of those different approaches together. So I'll talk you through this first before digging into some of the approaches we're thinking. So starting at the top, we have AGN events. You've got a black hole, it's growing. And I keep using the word event intentionally because an AGN isn't an object that persists in time. An AGN is an event in the life of the galaxy. And one galaxy may have multiple AGN events, multiple black hole growth events. And this actually makes our life difficult already, because if an AGN is turning on and off, how do we sort of control for that? So here's just a schematic model kind of base diagram again. Over the lifetime of a galaxy, you can just read the y-axis, the accretion rate. It's going to jump up and down. And maybe only ever so often you get a luminous AGN event that you'll be able to detect in your, say, X-ray system. So there's a whole bunch of literature trying to constrain the duty cycles of these AGN events. Where are they most common? Which type of galaxies are more likely to see an AGN event? Are there these dusty, obscured AGN events that we're missing in different searches? And this is a really important part of understanding the feedback process. Second group of observations that we sort of thought about was tackling this problem of energy to gas coupling. By which mechanism do you couple the gas from the AGN event to the host galaxy? I've already mentioned radiation, wind, jet. What's the relative importance of those? And then when it has coupled, how is that energy, mass, momentum, then carried by the gas? So here's a little montage. In the top left is a X-ray absorption feature, which can talk about these high velocity winds close to the accretion disk. The one on the top right is an emission line tracing molecular gas. We see these wings in the emission line profile. This is telling us something about the disturbed interstellar medium. The bottom left is showing us these ionization cones caused by the radiation of a luminous AGN episode. And in the bottom right, we see these jets in red and these X-ray cavities which may be inflated by these jets. So all of these different mechanisms and ways that energy is transferred into the host galaxy. Third category that we thought about that many papers look at is, can we see direct evidence for some impact of this AGN in situ on the host galaxy? So for example, here's a galaxy where there's a jet, which is shown in red. And then when you zoom in, you can see that the jet interacts with some gas clouds, and it's bright in H alpha because there's some localized boost of star formation. So that jet is colliding with the gas cloud and triggering a star formation. Likewise, you might find like a localized wind, and it's made a little cavity in the ISM. And I think it's important to distinguish this as a separate category to category 4, because these are probably localized transient events. So yes, they're interesting and physically important, but it might not be telling you the whole picture of the kind of global feedback process. That's where we move to category 4, and that's trying to find global long-term cumulative impact of AGN events. This is probably one of the most difficult things, because this is the accumulation of many AGN feedback events over time, and how do we find the evidence for that in the observation? And I think this is one of the things that's caused the most confusion in the literature, is trying to connect directly an individual AGN event with the global long-term impact on the host galaxy. I don't have time to go into that problem today, but Samuel Ward wrote a paper on this a couple of years ago, where we tried to tackle this by combining observational approaches and what we know from cosmological. However, today I'm going to focus on the second part of this feedback story and look at this energy gas coupling. And I'm going to break this into two parts. The first part will be using simulations to help guide observations of these AGN-driven outflows. And then I'm going to explore which of these mechanisms of energy injection may or may not be the most important. Okay, so the first part. How can we interpret the observed properties of AGN-driven outflows, and what can we use simulations to help us with that? Now, some of the key measurements that observational papers make of outflows is this. This is kinetic power divided by AGN luminosity, sometimes called kinetic coupling efficiency. So at face value, what this is asking is how much of my AGN luminosity is in kinetic power in my outflow. You may also replace the AGN luminosity with a jet power if you want to ask an equivalent question about jet. So you're asking with this, what's my viable driving mechanisms like jets or radiation? And then what's the potential impact on the host? And that's where you can start to infer, if this is efficient, and maybe I compare it to a simulation, I think this outflow has the potential to impact in the future on its host. These are the kind of measurements we might be making. Another common measurement to make is the momentum flux often parameterizes momentum boost. So this is momentum rate, the amount that divided by L over C, where L is the luminosity again. And that's asking how much of my theoretical momentum from my photons am I carrying in my own. And the reason that this observation is made is to ask questions such as, am I in a momentum driving regime or an energy driving regime? Am I conserving my momentum or my energy? I'm not going to go into the details underpinning that question. You can ask me if you want, but this is the kind of measurement that observers make to try and test these different ideas. And the third thing that's common to do, and you'll see in the literature, is to make outflow scaling relations. So take some outflow rate, a mass outflow rate, a kinetic power rate, and plot it as a function of AGN power to see if we can connect these two processes and understand how is AGN power connected to the outflows I see in a statistical sense. Well, what are the problems? Well, I often see these problems and these questions raised in literature, and I like to see if they're really a problem or everything's actually fine. So going to this first one, this kinetic coupling efficiency, there are many papers that appear to be finding very low coupling. And then comparing it to a theoretical prediction, say, these measurements are very low, therefore, I don't think these outflows can be efficient for people. And this momentum boost, likewise, there's a variety of conclusions in the literature, but the measurements are often lower than you may expect, for example, for quasar wind energy-driven models. And then going to these outflow scaling relations, there's a huge amount of scatter, in the literature, there's huge sort of disagreement in the shape and normalization of these relationships. So what's going on? What's the cause of these? Is there really a problem with our theoretical understanding? Well, unfortunately, it's extremely difficult to make these observations, and we mustn't forget that, right? We mustn't forget the limitations of what we can do with a single observation. So this is a multi-phase, multi-scale problem. This is just a schematic diagram thinking about the spatial scale going all the way from the black hole, the accretion disk, through into the surrounding medium, into the interstellar medium, and then onto larger scales such as the Earth-Moon medium or even the intercluster and intergalactic medium. We've got multiple orders of magnitude spatial scale there, which means you've got multiple orders of magnitude in time scale to worry. And on top of that, we have multiple orders of magnitude in temperature of the gas. This is multi-phase medium. So we have the cold material, the atomic material, might be tens, hundreds of Kelvin, through to the warm ionized material, which might be thousands, tens of thousands of Kelvin, through into the hot ionized medium, which can be millions or more Kelvin. So this is a multi-phase medium. It's very difficult to constrain simultaneously. In fact, it's impossible to constrain. So we mustn't forget this multi-phase, multi-scale problem. So how can we deal with that? The approach we're taking is to try and use the simulations to help us fill in the gaps of what we might not have in a single observation. So take, for example, some AGN injection model. Take your favorite model that you want to test. Inject this into some idealized hydrodynamic simulation of a galaxy disk. I'm interested in the outflows in the interstellar medium. Observe my simulation like an observer would, make the same sort of measurements, use the same sort of approaches, and then ask, did we infer the correct physical properties, given that I knew what went into my model? So we kind of looking at it like an observer and saying, if I did that, would I get back the right answer that I put in? So today I'm going to focus on this setup that was led by Samuel Ward, and this is in collaboration with Thiago Costa, who built the underlying model that we're going to use. So this is this solar model that Thiago created. We're going to use it to inject the quasar wind model, where based off what we know about quasar winds from observations, it's injecting energy and momentum in the very central region, and then we follow the hydrodynamics into a galaxy. In our fiducial model, we've got a wind of about 10 to the 4th kilometers per second, although we do vary the parameters, and we have a constant AGN luminosity in these simulations. We're using a repo, and we're reaching mass resolution around 10 or 100, depending on the setup, and that corresponds to spatial resolution of a parsec or so. And what's important is we set up the interstellar medium in different ways. So we first do like a smooth disk, it's sort of very idealized smooth disk in terms of distributing the gas. But we also have these fractal, clumpy, more realistic ISM setups. So we can get something that's got these gaps, these clumps, so we get these cold clumps as well as some hot and medium to create a more realistic galaxy disk environment. So this is just a little movie of one of these simulations of these quasar winds. You can see that we get these loosely collimated outflows above and below the disk. These are multiple phasing. And so in a qualitative sense, we've created a multi-phase high velocity outflow that's qualitatively similar to the kind of things that have been seen in the observation. We have these outflows that are venting through these paths of least resistance, through these gaps in the interstellar medium. And if we zoom into the cold clump, we find this cold outflowing clump embedded in this hotter medium. These are rapidly cooling, and you end up with this mixed fluid between the original ISM and the wind material. Now, today I'm not going to focus on the physics of the simulations and the formation mechanisms of the outflows. I'll refer you to Samuel Ward's paper for that from last year, and Ivan's paper that is about to be submitted discusses this in some detail. I'm going to focus more on how we can use what we learn from this, sort of plug that gap that we're missing from the observation. So we go back to the important parameters. Kinetic power, very simple equation, basically half mv squared, but we're dealing with rate, so it's the mass outflow rate. And the momentum rate, so we've got the mass outflow rate divided by times by the velocity. Both of these require a mass outflow rate. And if you read the literature, most observational papers will present you an equation like this for how they measure their mass outflow rate. Some new number B, which will depend on the scheme geometry, etc., times the mass in the outflow, times the velocity in outflow divided by the radius of the outflow. This is your kind of 101 equation for calculating a mass outflow rate. So I'm going to talk about first this velocity and this radius. Okay, so let's look at our simulations and think about those numbers. In the smooth disk case, everything's very nicely behaved. And the simulation kind of propagates in a way you get from an analytical model of a nice, everything spherical and well-behaved. And you get this inflating hot cavity surrounded by this shock material. You have this well-defined outflow as the shell expands. Within that shell, you get some cooling, and you get your multiple phases all traveling at a nice sort of consistent way at a specific radii and well-described velocity. But in a more realistic situation where you have a clunky structure, it's no longer a nice, well-defined, clearly defined outflow. You end up with this much more messy multi-phase outflow picture. What is the outflow radii of that? We don't know. So digging down here a bit more deeper, now I'm going to show you some phase diagrams of these two runs. So these are temperature versus velocity. And we're splitting this up very crudely into two phases. The hot phase, which is above 10 to the 4.5 Kelvin, which is largely invisible in observation. If you're lucky and you have really good X-ray data, you might be able to do something in the X-ray, but typically it's observationally extremely difficult to trace. And then the cold or cool phase. Now, I have a lot of debate, depending if I'm talking to simulators or observers, about how to name these phases. But this would include, at least qualitatively, warm ionized outflows, cold outflows, cool outflows. Pretty much anything that observers are doing would be plumped into this cold or cool. Not that we're simulating these directly, we can talk about that later. But basically, cold, cool is what we typically observe, hot is what we typically find very high. So let's look at these two regimes again. In the smooth disk case, we have this nice defined outflow velocity. Everything, all the phases are kind of traveling at the same velocity. But in the clumpy phase, in the clumpy example, we don't have this well-defined outflow. So we already have a challenge in terms of that equation that I showed you. What's the correct velocity to define when we're trying to measure this? Let's look at how the mass is distributed now. So this is a mass distribution as a function of velocity. The black curve is the smooth case. See this nice peak at a certain velocity. This is just for the cold gas. All of the masses, most of the mass is traveling at this velocity. But in the clumpy cases, which are the colored curves, we don't have this well-defined velocity. I've shown you three curves here because we experimented with different levels of clumpiness. There is some variation there, but it's not the dominant factor in what I'm going to talk about. So we're just clump all of those clumpy simulations into one regime. And what's very important here is we predict a lot of mass flowing at low velocity in this whole thing. And this is very important. And why? Because observationally, it's very difficult to find flow out. So we're expecting to see a lot of cold gas flowing quite slowly with a lot of the mass. Observationally, let's look at very crudely what might happen. So you get something like this. This is an emission line, an example emission line. It might look something like this. It's got some bright core, and that's very difficult to decouple whether it's outflowing material, galaxy dynamics, is it inflow, is it rotation? There are some sophisticated modeling you can do to try and decouple those things, but it's notoriously very difficult. You'll find a lot of papers, what they do is they say, I'm going to ignore that and just assume everything else is associated with the outflow. So these are the wings, the high velocity wings in the material. And when it comes to calculating your mass outflow rate, we'll just focus on those wings and assume the core is not outflowing. So to mimic that kind of limitation in the simulation, we created this minimum velocity to calculate the mass outflow rate. So we calculate the mass outflow rate above some minimum velocity. Now we've got the physical of a complete number, which is 10 kilometers per second. You can ask me why 10 if you want. But the one that we're trying to mimic the observational limitation is this 100 kilometers per second, just as a kind of a guide to where we might not be sensitive in the observation. So what's the impact of that? Let's look at this momentum boost parameter. So this is momentum boost for one of the simulations as a function of time. We've calculated the measurement pseudo like an observer would, split it into these two phases, the hot phase and the cold phase. That's the red and the blue. And the solid line is the complete outflow, calculating all of the outflowing cells, and the dashed line is with this lower limit on the velocity. So we can only capture an outflow if it's traveling greater than 100 kilometers. The important takeaway from this is if you're only tracing the cool phase and you're only sensitive to high velocity, you're going to get a much lower momentum boost than the true value, the total value. And in terms of this energy versus momentum driving, you're moving from an energy driving regime, which is these high values, into what would be inferred a momentum driving regime, which is these low values. So you may accidentally infer the wrong type of physical outflow driving because you're just missing velocities and you're missing phases in your object. And I'm not saying the observations are wrong. We just have to be aware of it when we're making the observations, that we don't overinterpret the jump from what we measure to what we infer. So we need to be careful when we're inferring different driving regimes. Now, something I'm not going to touch on, but I just flag, is also these things vary in time, of course. That's another layer of problem that we have to deal with. But I'm not going to worry about that too specifically. What about this kinetic coupling? So this is the kinetic power provided by the AGN luminosity as a function of time again, split by phase, hot and cold, red and blue. This time the yellow line or the orange line is the injection. So that's the kinetic coupling at the point of injection. 1.7% of the luminosity AGN gets injected into kinetic output. So that's what happens at injection, but what I might measure in my observation is 2 orders of magnitude lower than that because of the missing velocities and the missing phase. So I need to be very careful if I measure that number, that I don't say that my kinetic coupling is too low, or it means that it's too low to be efficient, or it's very low than expected from the simulation. Okay, so let's dig into this equation one more time. And this is now looking at the mass outflow rate. Sorry, the mass in the outflow. So we talked about velocity and radii, but we also need to think about how do I measure the mass. Here I'm going to focus specifically on one of the most common types of observations, which is the warm ionized outflows, which are typically traced by optical emission. And if you look at observational papers, the equation that you'll typically see is some number, which depends on the particular line you're using, times by the luminosity in the outflows divided by electron density. And that's one of the interesting parts of this equation, electron density, because it's notoriously difficult to observationally measure. And I'm showing some of Ivan's work, where Ivan did some refinement techniques so we could really refine these cold outflowing clouds and get super high resolution on those clouds. And here's just an example cloud from a run where the luminosity of the injecting AGN event is 10 to the 43. But this looks very different. If you increase the AGN luminosity, 10 to the 45, you see the structure already looks quite different. And if we go to even higher luminosity at 10 to 47, you see the structure is very different again. If we're increasing the luminosity, we're getting smaller, denser clouds in our outflow. And if you look at this across the simulation suite, there are different ways you can define these clouds, but it turns out it doesn't really matter. You see this increase in density as a function of AGN luminosity to the power of half. And again, I'm not going to dig into the physics of this today, but this behavior can be explained based on these cold clouds embedded in this outflow. I'm interested in what might that mean for my observation. So here we have mass outflow rate for 3 different simulations of 3 different AGN luminosities. That's the black for low luminosity, blue for medium, and cyan for high, as a function of density. That's the top panel. The bottom panel is this kinetic coupling. If I have some observational tracer of my electron density, for example, S2, which is one of the most common used, which isn't sensitive to low density, so it's not sensitive to below, say, 100 centimeters cubed. That's what this line I've just drawn on. For the lowest luminosity systems, I'm expected to miss half of the mass, just because I can't trace with my tracer the lowest density. So I'm potentially missing mass with my observation. And then going back to this kinetic coupling, the situation can get quite dramatic if I only have a trace of cold material that's very high density. I can infer a kinetic coupling that's potentially 3 to 4 orders of magnitude lower than the true number. So we do see papers that make these measurements that are incredibly low and then say, we've shown that outflows are inefficient, they're much lower than expected, they can't have an impact on the host galaxy. Well, that's a jump too far because we know our outflows are having a big impact on the host galaxy. They're driving these multi-phase outflows and really depositing a lot of energy. So just urging caution to understand what we are and aren't sensitive to in our observations. The last thing I'll show on this part is the scaling relations. So this is mass outflow rate versus AGN luminosity. These are some couple of compilations from the literature. Unfortunately, because of limitations in just the data that was available, and a constant electron density had to be assumed across the sample. Now, if we do have increasing densities, increasing luminosity, what's the impact of that on the scaling relation? Well, we would predict that the highest luminosity systems would have higher densities, which means that the mass outflow rate would actually be lower than the one first. So it rescales and knocks down the slope of this scaling rate. So ending part one there, we've been using simulations to help interpret the observation. So we are able to create qualitatively these multi-phase fast galactic outflows with a quasar wind model. But what these simulations are helping us understand is some of these observations that might be saying that the efficiencies are low, the momentum boosts are low, or maybe that's not the case. It's just because of missing information, and we can then need to scale back up these measurements to what the total values would be. I'm going to shift slightly to the second part and exploring this question about the mechanisms of energy injection. And this is something that has been interesting me for a while. For me, and people may not agree with me, that's okay, you can disagree. I think about AGN in two sort of main categories. One is radiatively efficient. So these are low accretion rate systems. You might have some sort of thick accretion disk. You have weak radiation. You're radiatively inefficient. You're not converting a lot of your mass to radiation. You typically might have a very strong jet. It'll be very bright in the radio. And you might have some slow wide angle wind. Now, sometimes this is called radio mode or something like this. Please don't use that term, because as I'll show you, radio is everywhere, right, across the board. Radiatively efficient is in the high accretion regime, such as quasars. Here, in terms of our energy injection mechanisms, we have a lot to choose from. So we have a lot of radiation, strong radiation, they're radiatively efficient. We have these high velocity accretion disk winds, and we also can have a jet. Sometimes it's powerful, strong, sometimes it's weak, but it's there. So the common assumption, or has been historically in that regime, that it's the radiation or the winds that are most important, particularly if you're talking about radio quiet, and I'll explain what that means in a minute. And jets have only been really considered important for radio loud. Well, I want to challenge that assumption. I don't think I have the answer for you today, but that's how we sort of started this sort of work. So let's think about the radio in quasars. This is where some of the terminology is a bit confusing, so hopefully this diagram helps. On the bottom axis, we have the radio luminosity divided by the optical luminosity. This is the traditional way to define something as radio loud or radio quiet. This dashed line, things on the right would be traditionally called radio loud, and things on the left would be traditionally called radio quiet. And if you're in the top right of this diagram, or anywhere on the right really, that would be radio loud. And there you're almost certainly dominated by powerful radio, quite nice and clear. But on this y-axis, we have the luminosity in the radio, which can't be attributed to star formation, probably AGN, divided by the star formation luminosity that's contributing to the radio. And what we say is if you're above this dash line, this above zero, you're AGN dominated in the radio. If you're below, you're star formation dominated. So we have this interesting group of objects here, which are not radio loud in the traditional sense, but they have excess radio emission above what you'd expect given the star formation. For me, these are really interesting objects, and we're finding lots of interesting things going on in these objects, and that's going to be the focus of the clash of different results I'm going to show you. I'm going to show you a series of results from different surveys that we're kind of working on this problem from the local universe, where we're using James Webb Space Telescope as part of the GAFOS survey, some local low-power AGN galaxies. Moving out to Redshift 0.1, we have this quasar feedback survey where we've just increased the sample from 40 to 70, and we're looking at the multi-phase gas properties, following up with high-resolution radio imaging. Moving out to Redshift 1, we're using DESTI and SDSS to build up large samples, tens of thousands of selected quasars, and then pushing out to Redshift 2. I'm involved in the super survey, which are X-ray selected AGN, and again, looking at the multi-phase outflows, following them up in the radio. And these are all different surveys, but there seems to be an emerging picture that there's something important about the radio emission when it comes to driving outflows, and there's something important about dust. So let me show you those. This plot here is taken from SDSS. This is local AGN, and it's cumulative distribution as a function of, it's the full width half max of the O3, but you can just read this x-axis as outflow velocities for now. The black curve are all sources, the blue curve are low radioluminosity, and the red curve is moderate to high radioluminosity. But I'll reiterate, these are not dominated by radio loud systems, it's these kind of radio excess systems. As part of our quasar feedback survey, we followed these up with high resolution radio imaging, and we start to see these interesting structures. If you push down to kiloparsecs or better spatial resolution, you start to see these collimated, maybe jet-like radio structures everywhere. If you don't have sensitive high resolution radio imaging, you wouldn't have realized. And what we find is amongst this quasar sample, at least 60% have evidence of AGN-associated radio imaging. We now follow that up with even high resolution radio imaging with E-Merlin, and even the kind of loosely collimated things, some of them start to become even more collimated. That's comparing the top panel to the bottom panel, and again, looking more and more jet-like. That's not necessarily all of the sources that do that. It's demonstrating, though, that if you push your sensitivity and your resolution, you start to see these interesting radio structures everywhere. And when we look at the multi-phase outflows of these sources, they seem to be connected to the radio in some way. So here's just one object. The left panel is showing you the velocity dispersion of the O3. The right panel is showing you the velocity dispersion of the CO. So the left panel is ionized gas, warm ionized gas, the right panel is cold molecular gas. In both cases, the high velocity dispersion seems to be spatially connected to the radio emission. And that seems to be the case across most of the samples. And this is consistent with predictions from simulations run by other groups, where you have these low power radio jets in the plane of disks and causing this turbulence. So maybe this is consistent with low power radio jets being an important driving mechanism. If we look at the larger scales of these systems, we start to see things that look a bit like these inflated cavities that you see in sort of more typical radio galaxies. So here's an example. We're looking at a map of the cold molecular gas and the contours of the radio emission. That looks like there's some jets, this bubble being inflated, and this cold molecular gas seems to be surrounding this bubble. But again, this is not a typical radio loud galaxy. This is one of these radio excess galaxies. We've been looking at this also at cosmic noon. So that can we see the same thing pushing to higher redshift? Well, the answer seems to be yes. There's a small pilot study that was just submitted where we looked using the super survey at redshift 2.5, again, finding these moderate low power systems. And it seems to be a spatial correlation between the most disturbed ionized gas kinematics and where we see the radio emission. The map here is showing you the velocity of the warm ionized gas, the contours of the radio emission, and again, it seems co-spatial. If we put these in the context of the more powerful radio galaxies, everything seems to be quite consistent. So caveat all of the problems I mentioned before about measuring outflow properties. If we measure the outflow kinetic power and we plot it as a function of inferred jet power, really it's just radioluminosity on the x-axis. It could be that the radio quiet system, which are these ones, are just scaled down versions of what we see in the radio loud. The last thing I want to mention to you is the thing about the importance of dust, which we don't yet understand. Dust also seems to be important in this whole picture. This is work that's been led by Vicky Fawcett from Newcastle. So what we're talking about here are quasars. This is from DESI and SDSS. So a typical blue quasar would look like this black line, this blue line at the top. And if it's dust reddening, you end up suppressing your UV optical light, and you end up ones that look more like this. We call these the reddened quasars. If we look at the radio detection fraction of these quasars as a function of reddening, we see this clear increase. So the redder that I am, the more dust I have, the more likely I am to detect radio. Now, just to reiterate, these are not radio loud systems, because if you just look at the radio loud definition, you don't see this correlation. This is dominated by this intermediate radio excess source. So there's something interesting about the radio emission associated with this dust. If you look at the radio SEG of these sources and you follow them up, so if you're plotting the flux as a function of frequency, these red ones seem to have very steep radio SEG. That's the most common thing we see, while the blue ones look flat or peaked. So these are more what you'd expect from a compact jet. These, maybe, we don't know, maybe this is something to do with shock that's being caused inside this system. this interpretation is still open. The last piece of evidence that there's an interesting connection between dust, radio, and outflows comes from an example from this very local survey where we've been following up with James Webb Space Telescope. So this is a local AGN. This is work led by Huda Haidar, our PhD students in our group. So here we're able to isolate the dust emission in the mid-infrared imaging from James Webb Space Telescope, which is the right panel. And on top of this, we're showing you the radio contours. You see that the radio and the dust seem very well aligned. And if you look at the kinematics of the gas, this is also where we see the outflow. So something is going on between the radio, the dust, and the outflows in these systems. I don't have the physical explanation for you yet. I'll be very interested if anyone has any ideas. So to summarize the second part, AGN-associated radio emission seems prevalent in typical quasars, not just radio-loud quasars, and especially seems prevalent when it's associated with ionized outflows and dusty quasars. What's the physical interpretation of that? Well, we're working on that to be continued. Some of our simulations are trying to now tackle that problem. Maybe there's a contribution from this small, low-powered jet. Maybe it's something to do with shocks that are driven by these outflows in the interstellar medium that boosts the radio emission. Let's find out. It's good to have a puzzle. Okay, I've got one more slide to show you. I have time for one more slide. Yeah. This is something completely different. Just in case you want to talk to me about it over drink. So this morning I went to House to Astronomy because a big part of my research, as Martha mentioned, is also on public engagement, accessibility, and I do this thing called data quantification, which is representing data with sound rather than with visual methods, or as a complement to. A lot of that came from my ambition to be more accessible. So we made a show called the Universe Tour of the Solar System, available in multiple languages, which we made with blind children, and we represented everything in the solar system with sound. So you can listen to the stars, listen to the planets, and learn something about the solar system. I'm also using it for my research. I wrote this review with Anita Zanella recently. I thought we'd show you one example. This was made by one of our team, James Traford. I'm sorry, it's the Eagle simulation, not TNG, but you could do the same for TNG. So you're going to see a movie of the evolution of time of the simulation, and the sound you're going to hear, hopefully the sound's still working. We've tied the star formation rate to a sound. So when there's a star formation episode, you hear a ping. And so over cosmic time, you'll be able to hear the cosmic evolution of star formation rate. So it'll get faster to cosmic noon, and then it'll decline. The pitch is tied to metallicity. So as the star formation becomes more metal rich, the pitch rises. You'll also hear this whooshing sound, and that's the feedback. So when we have a big feedback event, you'll hear a whooshing sound, hopefully. The first thing you'll hear is reionization, and then you'll hear some AGN later on. Let's see if this works. The sound. So reaching cosmic noon. Metallicity is increasing. Present day star formation rate dropping. An AGN going off. There you go. There's just a bit of fun to finish. So with that, I'll put up my main takeaway messages. So observational work on AGN feedback is maybe not as confused as you might have thought. Seems like it is, but hopefully we can convince you it isn't. Everything's fine. There are no problems. This first part, I talked about using a more realistic ISM, injecting a quasar wind model to build up these multi-phase outflows, and we can use those to help infer some of the challenges that we have in the observations. These are unavoidable challenges, but in tandem, we can kind of help in those interpretations and maybe not making the wrong interpretation. And then the second part, I kind of gave you this array of observations, which I don't fully understand, but it seems to show us that radio emission is very important in these more typical quasars, particularly associated with outflows and distant quasars, to be continued how to physically explain. That's the end. Thank
Thanks very much, Chris. I must say that acoustical representation of galaxy evolution was artistically also rather nice, I thought. But anyway, questions please from the audience, starting maybe with students. Any students or with first questions?
Very happy to take very basic questions. Very
No? All right. Well, why off?
we
Well, there's one in the front row.
not quite.
Hi, thanks, Chris, for the very nice talk. I'm wondering about the electron densities and the mass outflow rates. People usually use O3 to measure the mass, detect the outflows and measure the mass outflow rates, and then use sulfur lines like you measure. But O3 has much higher critical density than sulfur, so there can be dense regions where you wouldn't see the sulfur line, or so the actual densities for that O3 emitting region could be much higher, which means the masses would be lower. So does that make the problem worse, or?
Yeah.
So then how do we like, or should we just look at low density traces and not worry about the high density stuff at all?
Well, our predictions are said depend on the luminosity. So the higher the luminosity, the more important the depth regions are. But there is a lot of mass carried by the low density gas. So you do need a complete picture. In terms of knowing which traces are best, that's kind of the next step that we're hoping to do. So to apply some rates of transfer and do some direct predictions of different emission lines, taking into account critical density, things like this, to try and figure out which trace is the best one. My instinct is you're going to need an array of traces, some which are more sensitive to low densities, and some which are more sensitive to high densities, and try and figure out the relative contribution of those different density ratings.
Thanks. While everybody's thinking, let me ask a question related to this, moving on to the variety of line traces. I mean, you mentioned JWST spectroscopy. How important will the fine structure red forbidden lines be in this? Because they can, they can, of course, sample. For example, you've got things like oxygen 4 there. You've got neon 6 lines like this, which could actually certainly get into the 10 to the 5s and maybe borderline 10 to the 6. I mean, is that something that you're thinking of?
Yeah, so I don't know the detailed physics of those lines, to be honest, but exactly they could be very helpful for tracking these phosphophases. So if we can find good traces of these phosphophases, that's going to be very helpful because we are expecting a lot of energy to be carried in these phosphophases. How you go from the measurement to a reliable energy or mass, I don't know. That will definitely need some thought, but any tracer that can trace phosphophases, even indirectly, would be very helpful.
Right. Next question. Then let me ask another. Oh, there is one. Yep. Good. Where was that?
Thank you for the talk. My question is about point 4 in your introduction that you didn't touch, but I was just curious if there is any way that we can quantify this long-term impact on AG and on galaxies.
Yeah, so Dylan was just showing me some nice results there. So there are, depending on your feedback model, there are different potential imprints on the galaxy population. I think what you need to be looking at is not AGN, but the kind of galaxy population as a whole. And depending on how your feedback works, you might expect, for example, different distributions of the baryons and the halos after they've been redistributed. You might get different predictions of how quickly the star formation is quenched, so if you can get some star formation history traces. I don't know the best ones off the top of my head, but that's sort of thinking out loud. I expect these different models have quite different predictions of their signature that they leave behind, either on the gas or on the stellar populations. And I think that will be the way to find it, looking at the galaxy populations as a whole, not looking at AGN, because an AGN is just one event that you happen to catch.
Okay.
Beautiful talk and really instructive. I think I got a bit confused on your point 3 here, where you were showing the alignment of the radio emission in some sources with the oxygen 3 and the CO emission.
Yeah.
I got a little confused on where yes, that's so. For the radio emission, you're 100% sure it's AGN emission in this case.
Definitely APN,
Okay.
but that's as far as I'm willing to say.
Okay. Yeah, I'm a bit confused on why the GN emission is perpendicular to the outflow emission.
Yeah, so I kind of strayed over some details here. So what we think is finding a lot, and also other groups are finding the same thing, that it's slightly just leaving a weight of turbulent material behind them. And that's the same that they see in the simulation. So in the simulation, the red colors are the high velocity dispersions, which are being left behind as the jet propagates through the disk. It's kind of leaving this turbulent weight behind it. And that's what we think we're seeing here. So just behind kind of terminus of the jet, if it's a jet, it's got this expanding bubble of turbulent material behind it.
That makes sense, but why not in front of it then?
So here we do see a big velocity jump at the terminus. So if you look at the bulk velocity here and the bulk velocity here, there's a sharp jump in the velocity.
A question down here.
Thank you very much. Beautiful talk. When I see the summary slide, maybe it's a very naive question, but I see outflows and dusty quasars, and I think of mergers. So have you seen if in your radio, I'm calling radio bright sample, do you see like a large merger fractions, or what is the environment there?
We haven't done anything on mergers, so I don't have any information on that. So that's something interesting.
Okay, we have one question on Zoom from Christian Fent. While we're waiting for him to type it, I'm ask Dylan to continue.
Thanks, Chris. So I like very much your emphasis on AGN event. And my question is about the dichotomy of the radio loud and the radio detected.
Yeah.
So do you picture that both of those phases occurring within a single AGN event, which is could this be an evolutionary progression in time between these two states? Or do you picture it as something different where maybe a single AGN event is either radio loud or not?
Yeah, so when we say radio loud here, I'm going to assume you mean having a powerful relativity set. So I think that might be independent. That might sometimes happen independently of the other events where you might not find a powerful relativity jet, but you've still got maybe a relatively efficient episode where you deploy big energy to wind, for example. I don't think you necessarily simultaneously get all of this happening. Some events may be more in the relatively inefficient mode with powerful jet, and some may be in the relatively efficient mode. But my point is you get radio emission all the time, and it may be tracing different physical processes.
So Annalisa has a question.
Chris, thank you very much. So in the simulations, beyond all the effects that you mentioned, we invoke AGN feedback first and foremost to quench star formation in massive galaxies. And I completely hear you and thank you for all these clarifications on how to interpret data. Do you think actually in the literature there is data-driven smoking gun that AGN are actually quenching star formation?
What would that look like? That's the problem in somebody's not basically. So what we concluded in this review was there's nothing to say that isn't what's happening. I don't think there's any evidence that contradicts the qualitative picture that we have that AGN feedback important. I don't know what the smoking gun would be. I mean, what would that be? I think all we can do is take a specific model, get a prediction out of it that is sensitive to the agent feedback, that's independent of the tuning, and see if that's what the real universe looks like. Can't imagine one single smoking gun. Maybe someone has an idea, but I think that sent us on a lot of people were trying to look for that, but they didn't know what they were looking for. So, I don't know, kind of looking for something we don't know what we're looking for.
Yep, I think.
That's right. I don't think there's anything that's inconsistent with that picture that we have.
Okay, we got two more questions. I'm going to first of all read out one from the online from Christian Fent. And Christian is asking, I'm wondering whether the structure of the dark matter halo has an impact on your interpretations. Definitely gravity will affect the dynamics. So, the question.
The question was, structures that matter halo will impact the interpretation. I don't know which.
No, oh, okay. Do you, Christian, do you mean the near-in halo or the far-out halo? Okay, while Christian's thinking about that, I'm going to go to the last question in. So, last question in the hall.
Oh, yeah. So you were showing this plot where you separate the radio loud and the star formation that you would expect versus the radio that you would transform into star formation. This plot, yes. So if you take these, well, undetected, you mean the things that are not AGN, or what do you mean undetected? Undetected as in radio, non-radio.
Sorry, that means you can't detect anything in this bottom left.
All right.
Sensitivity limitation.
Okay, so if you color this by the velocity width of the gas in O3, for example, and you take the highest ones and the highest ones in the lowest left corner that are supposed to be not AGN, and you take the most dust attenuated, and you repeat this exercise of deep radio observations, would you expect to have these collimated structures?
Yes, so I think if you dig deep, you'll find an AGN potential. You'll find radio emission. Well, not necessarily, depends on deep cycles, of course, but a certain fraction, I expect you to find some AGN emission in movement.
Right. Yeah. Thank you.
Okay. Okay. So I think Christian's basically saying he'll talk to you later about this. I think you're going to meet up at some point. So it's probably best to leave it till. So it just remains before we thank Chris, just for a couple of announcements. First of all, Marco Albon, maybe Marco would like to say something about a students' meeting and dinner.
So we have organized the usual students' drinks at Bar Centrale. It's just 7-ish minutes walking distance from here. So if you want to join, please let us know at the end. So far, I have not seen anyone formally registered in the Google Docs document, but I've had someone approached telling that it's interest, but please let me know now. Let us know now that you're interested, also for the dinner.
Yeah, I think you were tentatively thinking about the Knossos Gaststätte on the Berghammerstrasse, right, for dinner? That was the intention. So if anybody wants to join, just make yourself known at the bottom here, and of course, then Marco can sort of make some arrangements. So next week, this final announcement is the colloquium will be by Nicole Reindl locally from the Landessternwarte. She will be talking about unlocking the various evolutionary pathways of sunlight stars. So do come along then. So Chris, this was a very thought-provoking and very artistically interesting and scientifically also extremely interesting. And I think a lot of us will appreciate very much, especially people like me who don't work in your field, the clarity that you can put into this obviously very complex observational situation. Thank you very much.